Hi guys, welcome to Chapter 2, Limits and Their Properties, Section 2.3, Evaluating Limits Analytically. In the last section, we learned how to evaluate limits numerically and graphically. And based upon what we saw within the homework problems and some of the other things we did last class, you should be able to figure out what these nice limits are equal to. So I'd like you to pause the video right now, and I'd like you to consider these three rules. The limit as x approaches c of b, where b is a real number, the limit as x approaches c of x, and the limit as x approaches c of x to the nth power, where n is a positive integer. I'd like you to consider those. So pause the video right now and see if you can figure these out on your own, what they should equal. Go ahead, pause the video. I'll be here when you get back. So let's consider this first one, the limit as x approaches c of b. That is essentially a horizontal line, isn't it? Right? B is some number, so we have some horizontal line. And if you think of it, no matter where I go, any number c, if I go someplace on the horizontal line, it's always equal to the same y value. And what value will that be? Well, that's whatever b is equal to. So the limit as x approaches c of b, where b is a real number, equals b. What about the second one here? The limit as x approaches c of x. So if you think about what that looks like, right? That's the line. That's the line, y equals x right here. No matter where I'm at, some c value, what's it going to be? It's going to be the same input as it is an output. So I'll get the same value. So the answer to this is c. The limit as x approaches c of x is equal to c. Okay, the last one. X to the nth power, where n is a positive integer. Well, again, if you think about what we had talked about last class, the easiest way to figure this out is to just plug c in for x. What do you get? C to the nth power, whatever it is. Not bad. These three very basic rules will unlock a lot of doors for us as we work through these problems. And so will a lot of these properties that you see here. I've taken this from page 79 in your textbook, so you can take a look at this. If you're really interested in a proof, you can always go to Appendix A that's in the back of the book, or look up the proof to these on there. But these are things that are pretty important. We know that scalar multiplication of limits works. We know that I can add and subtract limits and get the same thing. I can multiply limits. I can divide limits. I can raise a limit to a power, and I'm going to be able to end up with something that logically makes sense. Let's take a look at some of these properties in action. So here we go. The limit as x approaches to of 4x squared plus 3. So according to my rules that I just saw on the last page, I can actually take this limit and I can break it apart using the idea that the sum will work. So I can take the limit of the first part, limit as x approaches to of 4x squared, and I can add that to the limit as x approaches 2 of 3. That's really nice. Another thing that it says, based upon the scalar multiplication, it says that I can take this 4 and move it out front. So I can have 4 times the limit as x approaches 2 of x squared. And again, plus the limit as x approaches 2 of 3. And then again, based upon what I know about these rules, is it should be really easy to evaluate them based upon those basic properties that I had at the front. So let's see here, 4 times, and if I think about it, the limit as x approaches 2 of x squared, well, that's just going to give me 4, okay, plus the limit as x approaches 2 of 3, well, that's 3. So what do I have? That's 16 plus 3, which equals 19 is how I evaluate that limit. And if you looked at the graph or you looked at the table of values, you would get the same answer. But you know what? Do we really need to go through all this? No, we don't. All we really have to do is take 4 times 2 squared plus 3, and we get 19 right out the bat. That's kind of one of the things that's really nice and important. You need to make sure you plug the number into the equation first and see what you get. If you get something nice and this equation isn't anything weird, you can trust the value that you get as the output value to evaluate the limit. Let's take a look at a couple more examples. Okay, the limit as x approaches 1 of x squared plus x plus 2 over x plus 1. So because I'm approaching 1, there's nothing weird happening to this function at 1. Negative 1 would be a different story, but not 1. 1 is perfectly okay. So what I'm going to do, I'm just going to take and I'm going to plug 1 into my equation. So I get 1 squared plus 1 plus 2 over 1 plus 1. I evaluate that. I can simplify that down and come up with the answer of 2. Not anything fun and exciting here, right? I don't have to use all those properties and show a proof. This is good enough. This math is just as good as doing all those other individual properties. Number 3, the limit as x approaches 3 of the third root of 2x squared minus 10. Again, nothing fancy going on here. Just evaluate. Just plug the number into the limit and simplify. So let's see here. 3 squared is 9 times 2 is 18. 18 minus 10 is 8. And the third root of 8 is equal to 2. Nothing crazy going on here. And we can do this with trig functions too. Nothing going on here, anything weird. So I can just evaluate the tangent of 0, and the tangent of 0 equals 0. For the second one, let's hear that's pi times the cosine of pi. The cosine of pi, of course, is equal to -1. So this ends up being negative pi. And the last one, what is this? Ooh, okay, now remember, this really means the sine of x, that quantity squared. We can't take that for granted. So just remember that. So then we're really doing the sine of 0 squared, which of course is 0. Okay, not bad. If it works for trig, it also works for inverse logs and log functions. So again, we just plug our numbers in. So here we go. We got -1 times e to the negative x, or negative first power. I can simplify that down. I get -1 over e. That's a good enough answer right here. That's simplified down. Go look at the next one. The limit as x approaches e of the natural log of x to the third. Just plug it in. We can rewrite this as 3 times the natural log of e and come up with just 3 as my final answer. So there are some more limit theorems, if you really want to read them, that are in section 2.3 again, somewhere around pages 80 and 82. You can look at the theorems, but I've illustrated these already with the examples we've gone through. All right, let's take a look at one that's a little trickier. So the limit as x approaches 1 of x to the third minus 1 over x minus 1. So I'm hoping that you've already figured out what the issue is. When we plug in 1 into my equation, I end up with 0 over 0. And I'm not so worried about the 0 on top, but I'm worried about it right here on the denominator. So this actually becomes undefined at 1. But remember, it doesn't mean that the limit is undefined. Okay, it just means my function is undefined. So we have to dive into this problem a little bit more to figure out if the limit is defined or not. So this is where we get a little fancy with our algebra. We can evaluate a limit, or based upon those properties, we can evaluate an equivalent form of the same limit. What do I mean? I mean, hopefully you notice the top is factorable. I can factor that down because that's a difference of 2 perfect cubes. So I can factor that down to be x minus 1 times x squared plus x plus 1. And the denominator is still x minus 1. Because of that, I can cancel out what's on the numerator and the denominator that's the same after I factored. And that means that the limit of x to the third minus 1 over x minus 1 is the same as the limit as x approaches 1 of x squared plus x plus 1. That we can evaluate. That we can come up with an answer to. And if you take a look at the graph, you're going to see that this, in fact, does work. So you want to make sure that you've always tried to plug in the number first to see what you end up with. And if you can't evaluate it or something weird happens, that's when you take this analytical approach, where you actually factor things and look at an equivalent form of the limit. Take a look at this. The limit as x approaches 1 of x to the third plus x over x minus 1. Again, you should, when you plug in 1 into this equation, see that the denominator is undefined. We get 0, which makes this function undefined at 1. So let's look at an equivalent form. So we'll look at the limit as x approaches 1 of, well, factor the top. That's x plus 1 times x squared minus x plus 1 over x minus 1. Uh-oh, now here we have a problem. In the other, we saw that this and this matched, but here they don't. So what happens? Well, we don't worry about it. We can't simplify this at all, so the limit here does not exist. So let's take a look at the difference between these two graphs. Here's the graph of x to the third minus 1 over x minus 1. Notice there is a hole right here. There is a hole at the point 1, comma 3, which, if you remember, we were looking at the limit as x approached 1, and you come up with the value of 3 out here for the y value. But here you have the graph of x to the third plus 1 over x minus 1. And you'll see instead of having a hole at 1, we have an asymptote. So we have to be really careful with how we're defining these functions, and the limit will always tell us what we have going on here. Okay, what about this one? Still, when we plug in 0, you see that the denominator is undefined. But I'm not sure how I'm going to deal with this because it's not like the top is factorable. So I can't factor the top, and it's not like anything's going to simplify down really nicely with the denominator. I wonder if the limit even exists at 0. Let's take a look at the graph. So based upon what I see here at the graph, I do think the limit exists because if I look at it and I look at as what happens as x approaches 0, it looks like it's a value. As a matter of fact, I'm fairly certain that the number is 1/2. So how in the world do I look at this equation and come up with the answer of 1/2? There has to be a way. So I want you to remember that since we can't do anything with this, we can't simplify this. However, we can actually evaluate the limit of this or any equivalent form. So we just have to be smart about the equivalent form we pick. This is where some different hints and tricks come in. So what I'm going to do is I'm going to take and I'm going to multiply the top and the bottom by the complex conjugate. That's something I haven't heard since pre-calc when we were talking about complex numbers, but they also work with radicals as well, and it's a nice way to eliminate a radical, not on the denominator like we're used to with problems, but here on the numerator. So when I multiply out the top, I'm going to get the first. If I multiply the first, the square root of x plus 1 times the square root of x plus 1, I end up with just x plus 1. Then I get minus the square root of x plus 1 plus the square root of x plus 1 minus 1 all over x times all that crazy stuff right here. Okay, on the top, what happens that's nice is these radicals disappear on the top. And the plus 1 and the minus 1, they cancel each other out too. So when I simplify this down a little bit more, I'm left with x over x times the square root of x plus 1 plus 1. And then again, my x's will cancel out. So one more time simplifying it down, I end up with the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. This is something I can plug 0 in for and end up with an actual answer. So let's see here, what do I get? I end up with, check that out, 1/2, the thing that I thought I should get the whole time. How about something like this? The limit as x approaches 0 of sine of x over x. Multiplying by a conjugate's not going to help me here. I'm not really sure what to do. Let's look at a graph. The graph's pretty helpful here because it's very obvious that as x is going towards 0, my limit is actually going towards the number 1. But how do I figure this out analytically? The answer to that is a little more difficult than what we can do algebraically. What we do is we look at two different functions. We look at one that is below the sine of x over x. That's this curve. That's the sine of x over x. I didn't change anything there. But the blue curve is something that's below that function. And I'm not looking for the whole thing, rather just around 0. What happens around 0? The correct calculus term is in the neighborhood of x equals 0. So if we look at that, this blue curve is below the sine of x over x. And that is actually the cosine of x. And my black curve up here, again, that's above the sine of x over x, around in the neighborhood of x equals 0. So, and that's actually the function x squared plus 1. So what we can do is we can use something called the Squeeze theorem. The Squeeze theorem. This is all outlined in your book if you wanted to read exactly what it is. But the gist of it is this, is if we have a function, h of x, that's always less than my original function, f of x, and that is less than another function, g of x, and the limit as x approaches c of h of x equals some number, which also happens to be the limit as x approaches c of the function g, then I can conclude that the limit as x approaches c of that middle function also has to be L. And that's what we got going on here. If we look at the limit as x approaches 0 of x squared plus 1, what's it going towards? It's going towards the value 1. The same thing with the blue curve, the cosine of x. The cosine of x, as my values get closer and closer to 0, well, that's also going towards the same value, 1. So, since the curve that's above it is going towards 1, and the curve below it is going towards 1, then the function that's in the middle has to obviously be going to 1 as well. This is just one of those rules that you should probably, it'll save you a lot of time. And again, here's the squeeze theorem actually written out for you. But I think looking at the explanation or thinking about the explanation is so much better. There are really just two of these trig limits that you should have memorized, and they're here on this next slide. The sine of x over x as x approaches 0 is equal to 1, and the limit as x approaches 0 of 1 minus the cosine of x over x equals 0. And again, I've outlined both of these here for you. Let's see how they apply to an actual problem. So here we have the limit as x approaches 0 of tangent of x over x. Well, that's nothing that we looked at in the previous, so is this another one I have to memorize? It's not. You just have to algebraically be able to manipulate this limit. So again, how can I rewrite tangent? Ooh, tangent is sine over cosine if I remember some of those trig identities, which means I have sine of x over cosine of x all over x. And if I remember exactly how to write that, I can convert that and write the limit as x approaches 0 of sine of x over x cosine x. And again, if I split that up, I can rewrite it the limit as x approaches 0 of the sine of x over x times 1 over cosine x. And again, thinking about it using those limit properties, the limit as x approaches 0 of sine of x over x, hey, I know what that is, times the limit as x approaches 0 of 1 over cosine x. This first one, that's just 1 times, well, let's see here, the cosine of 0 is 1, so this ends up being 1 over 1, which is 1. So my final answer, the limit as x approaches 0 of tangent of x over x, that equals 1. What about this? The limit as x approaches 0 of sine of 4x over x. Well, see, here's the deal. If this and this match, it's 1. The problem is there's no number here. So what can I do? I can algebraically manipulate this. I can multiply by a form of 1, 4 over 4. Right? Multiplying by 1 doesn't change the problem. And that's all this is. 4 over 4 is a form of 1. And now watch as I rearrange things. So this 4 is a constant. I can bring that out front. So 4. Then the limit as x approaches 0 of the sine of 4x, and I can put this one right over here in front of that x, the sine of 4x. What do I end up with? 4 times, that's 1, which gives me 4. Not bad. That's all I have for you guys now. If you want to take a look at some of these practice problems, they start on page 87 in your textbook, and you do these selected problems as part of your homework. If you have any questions, please do not hesitate to ask. Good luck.